our last exponential application is about Newton's law of cooling. So when an object is placed in a warm or a cool room, it's trying to warm up or cool down to that temperature of its surrounding. We have this formula to help us discover the actual temperature of the object at any time t. Originally, Isaac Newton was the one who discovered this. That's why it's called Newton's law of cooling. And he discovered it when he was looking at the relationship of cooling objects of the body. So if we break down what all these letters and things represent, T of t is just saying the temperature at time t. But T sub s represents our temperature of the surrounding area. So it's basically our outside temperature or the room temperature, whatever the surroundings are. T sub 0, that sub 0 is always going to be initial. So that's the initial temperature of the object of whatever we're talking about. Minus T sub s again, so the surrounding temperature again. E is always just E. It's not a variable in this case. To the negative kt. Well, k is a constant, and it's just going to be a constant that changes based on whatever object we have. So when we were talking about exponential decay, we had a half-life thing, and every half-life object thing has a different half-life. So same kind of thing, things cool at different rates. So k is a constant depending on that object. So we're going to actually have to solve for k often. And then t is our time. So suppose that a dead bald eagle was found in the woods and its temperature was 80 degrees Fahrenheit. The temperature outside that day was 60 degrees. 2 hours later, the temperature of the bald eagle dropped to 75 degrees. We're going to find k and then find the time since death that the body was found. All right, and it does give us that the living temperature of a bald eagle is 105 degrees. So when we think about what's really going on here, it is an exponential decay function. The initial temperature of a bald eagle is 105. But it's decaying, and it's trying to reach that room temperature or outside temperature of 60 degrees. So what we're going to have is this horizontal asymptote at 60, because it's not going below the regular temperature outside. So our decay function would be exponentially trying to decay closer and closer to that 60. What we know is that it was it was 80 degrees at whatever time we found it. So we know that it's going to reach 80 at some point. And then 2 hours later, it's going to drop to 75. This is the important part, is that we know that the time frame between here and here is 2 hours later. We need two temperatures and the time between them to get that k that's a constant. So there's going to be a lot of algebra to solve this out, but let's see what we have when we're plugging this in. So T of t. 2 hours later, it's 75. There's a temperature at a certain time equals the surrounding temperature. Well, the surrounding temperature is 60 plus our initial temperature minus the surrounding. Our initial temperature is actually 80 right now, because initially I know we were 80 and then 2 hours later we got to 75. So we're going to leave that at 80 minus 60, that's the surrounding temperature, e to the negative k, and then t was 2, because we're talking about 2 hours later. So all of this is a lot of algebra to solve, but we can simplify it a little bit at a time. So 75 equals 60 plus 80 minus 60 is just 20, e to the negative 2k. If I want to solve for an exponential, we want to get the exponential part by itself. I do need to divide by 20, but not until I subtract 60. So we're trying to get this part by itself by getting rid of 60 first. 75 minus 60 is just 15. So 15 equals 20 e to the negative 2k. I undo the 20 by dividing this time. So 15 divided by 20, if you want to use your calculator, you can. Should be 3/4. So 0.75 or 3/4 equals e to the negative 2k. Just like all the others, we're solving for the exponent, so I need to convert to a log, but we're in base e, so it's a natural log of 3/4 equals negative 2k. We divide by negative 2, so k is the natural log of 3/4 divided by negative 2. That's what we're going to have to approximate because it's not going to be a nice value. So natural log of 3/4 divided by negative 2 is roughly 0.1438. So 0.1438. We needed k because we need to know the constant to work out any other part of the equation. So we found k. Then it says, find the time since death that the body was found. At that point, we know that the initial amount was 105. We want to know how long did it take to find it, which was at 80. So it's really trying to find this temperature between 105 and 80. Not the temperature, the amount of time between there. So if 80 represents the time at X amount of hours later, then the surrounding temperature is still 60 plus our initial temperature, which was 105, minus the surrounding, so 60, E, but this time I know what K is, so it's E is negative 0.1438 T. We're trying to solve for the amount of time that's passed when we found it at 80 degrees Fahrenheit. So I would subtract 60 to get 20 equals, and I can work out that as well. 105 minus 60 is going to be 45, so 45 e to the negative 0.1438 t. Divide by 45. If you want to use your calculator, do 20 divided by 45. You get a value that's not going to be nice if you just stop it off. So that's why we use a fraction instead. So 4/9 equals e to the negative 0.1438 t. When I convert into a natural log of 4/9, I get 0.1438 t by itself. Sorry, that's a negative 0.1438 t. And then we divide by that negative 0.1438. So t is the natural log of 4/9 divided by negative 0.1438. Let me see, what is that approximately? So the natural log of 4/9 divided by negative 0.1438 is roughly 5.64 hours later. So it did say find the time since death. It was 5.64 hours. People would use this in forensics to calculate the time of death for something if they can get the temperature reading. All right, in example 2, we now have a hot bowl of soup. It's served at a dinner party. It starts to cool according to our Newton's law. We actually have the equation this time. We want to know what is the initial temperature of the soup. Based off what was given to us, look at where we have this. The initial temperature is T sub 0, but it's not written in that exact format because it's already been simplified. So to find the initial temperature, we can just do T of 0. Make it easy on ourselves. T of 0 would be 68 plus 138e to the negative 0.0487 times 0. And just plug that into your calculator, see what you get. So 68 plus 138 e to the negative 0.0487 times 0 is 206. So our initial temperature was 206 degrees Fahrenheit. What is the temperature after 10 minutes? Means I'm just plugging in 10 for T. So T of 10. 68 plus 138 e to the negative 0.0487 times 10. 68 plus 138 e negative 0.0487 times 10. 152.8. And then after how long will it be 100 degrees? So this time we're solving for T. I can plug 100 in for our temperature. 68 plus 138 e to the negative 0.0487 T. I subtract 68, so 100 minus 68 gives me 32 equals 138 e to the negative 0.0487 T. You would want to show all this work. So 32 divided by 138 comes out to be this decimal approximately. Let's see, that fraction is 16 over 69. Equals e to the negative 0.0487 T. We convert to our log, so natural log of 16 over 69 equals negative 0.0487 T. We would divide, so T, let's bring this back up here. T is the natural log of 16 over 69 divided by negative 0.0487. And we can find that approximation in our calculator. So natural log 16 over 69 divided by negative 0.0487 is roughly 30.01, or just 30 hours. All right. Actually, not hours. Sorry, minutes. We were talking about minutes earlier. So 30 minutes. That would not make sense if it took 30 hours. That's why we got to focus on our units. Okay. Our last two examples here, you can pause and try them on your own, or you can work through them with me. Pause at whatever time you need to. So Reagan and Chris both came to visit the math department at 9 a.m. one day. They began in the seminar room where they each poured a cup of piping hot 200-degree coffee. There's our initial amount. They took a 10-minute tour of the department and returned to the seminar room to drink their coffee, which was now 150 degrees. This is where I'd stop and just start to make sense of what's going on and create a graph. So our graph would say we started the coffee out at 200 degrees. It's going to decay. So we're going to be doing that asymptote somewhere. But we know after 10 minutes, we reach 150 degrees. So I can say, let's put our 150 here. The amount of time between those two things is 10 minutes to reach 150. Then it says, Reagan begins to drink her coffee, but Chris chats in the hallway. Chris refuses to drink his coffee if it falls below 105 degrees. Very pretentious. How long can he talk in the hallway before he throws out his coffee? So we're looking for, he's going to wait some amount of time. So how long between the 150 to 105 degrees is going to pass? That's an unknown amount of time. It does say that assume that room temperature is 72 degrees. So there's our asymptote. It's going to approach this 72 degree mark eventually. Now let's kind of work through what the equation is. To remind yourself, is T of T equals T sub S plus parentheses T sub 0 minus T sub S e to the negative k t. To do this formula, we first have to solve for k. I can't calculate anything without knowing the constant. To find a constant, I have to know two temperatures and the time between them. So that's why we have this 200 and that 150 that happened in 10-minute span. So after 10 minutes, we get to 150 degrees. So the T of T is saying the time at a certain, the temperature at a certain time equals the temperature of the surrounding, which is 72, plus our initial temperature, so 200, minus the temperature of the surrounding again, so it's 72, e to the negative k, we don't know, but t we do, because t is saying 10 minutes later, we reach the 150 mark. We solve this out. So let's subtract 72. 150 minus 72 is 78 equals, and then we just do 200 minus 72. So 128 e to the negative 10k. If I divide by 120 or 128, I'd have 78 over 128 equals e to the negative 10k. You can simplify the 78 over 128 to 39 over 64, but we're going to be taking the natural log of that 39 over 64. And it equals the negative 10k. So I divide by negative 10 to find out what k is. The natural log of 39 over 64, close it out, divided by negative 10 is 0.0495. So we found out what k was. Now we can use that to actually find any temperature, because we want to know how long it's going to take for him to reach this 105, because it says how long can he talk in the hallway. He stopped here at the 10, and this is all of him talking in the hallway. So if we find, let's do it over here, 105 is the temperature we're looking for. 72 is still our outside temperature, plus I'm going to change the initial temperature from 200 to this 150, because now we're looking at this time frame between these two values. So 150 minus the 105 e to the negative 0.0495 t. We found the k, we plug it back in. If I subtract 72, 105 minus 72 gives me 33. 150 minus 105 should be 45. E to the negative 0.0495 t. We divide by 45, so 33 over 45 equals e to the negative 0.0495 t. We can convert to a log and simplify your 33 over 45 if you want, but it'd be 11 over 15. You can also leave it as 33 over 45 for right now in your calculator. So negative 0.0495 t. All we need to do is divide by that 0.049 to get our t. So I do natural log of 11 over 15 divided by negative 0.0495 is roughly 6.26 or 27. And then this is all talking about minutes. So he has about 6.27 minutes to sit here and talk in the hallway until he has to report out because it can't go below 105 for him. The last one here, a roast turkey is taken from an oven when its temperature had reached 165 and is now 145. 15 minutes later, the roast is 120 degrees. How many minutes will it take the roast to reach 95 degrees if the temperature of the room is 72? So again, we want to draw out this graph. The room temperature is 72, so let's put in that asymptote. It was taken out of the oven at 165, so that's got to be our initial temperature. And it's going to decay from there. So based off what we know, it was taken from the oven when temperature was 165 and it's now 145, but we don't know how much time has passed. It does reach 145, so that's an unknown amount of time. And then 15 minutes later is going to be at 120. So now we get down to 120, and the amount of time that has passed between here and here is 15 minutes. We need a time and two temperatures between that time. So that's what's going to help me find K. Plug in what we know. T of T is the temperature at a certain time. The thing I know is that it reaches 120 after 15 minutes. So 120 equals 72 plus 72 is our surrounding temperature, the initial temperature. Now, I said 165 was the real initial temperature, but we don't know the amount of time between those two things. So we change that to 145 because that can be the initial temperature 15 minutes later. All right, so 145 minus 72 e to the negative k times t, and t is 15 minutes later. If we simplify this a little bit, I could subtract 72, so 120 minus 72 is going to be 48 equals 145 minus 72 is 73 e to the negative 15k. We would divide by 73, so 48 divided by 73. It doesn't reduce any. We can just leave it as 48 over 73 equals e to the negative 15k. Since we're solving for the exponent and our base is e, we turn it into the natural log of 48 over 73 equals negative 15k. We divide by 15. So in my calculator, the natural log of 48 over 73, close it off, divided by negative 15, gives me k to be about 0.027. That 9 is going to round up, which makes that 28. Okay. So we found out what K was. That allows us to figure out how many minutes from the time the roast left the oven did it take for the roast to reach 95. So eventually it's going to reach 95. And we want to know the time between the 165 and the 95. So I'm going to say 95 equals 72 plus our new initial temperature is not 145 anymore because now I'm looking at actually leaving the oven. So 165 minus 72 e to the negative 0.028, so 0.028 is kt. We solve these little things. So I can subtract 72. 95 minus 72 is 23, equals 165 minus 72 is 93. E to the negative 0.028 t. We divide by 93, so 23 over 93, that's not going to reduce any, equals e to the negative 0.028 t. Convert to a log, so natural log of 23 over 93 equals negative 0.028 t. And we divide, so natural log of 23 over 93 divided by negative 0.028 is 49.896. That 6 would round up, so roughly 49.9 minutes. Or 50 minutes if you want it, if it told you to round to the whole minute.